question number 6. So find the volume of the described solid S, a cap of a sphere with radius r and height h. Okay, so they're asking us to find the volume of this, I guess, hemisphere at the top of the sphere with height h and radius r. Okay. So in my previous lessons, I covered how to calculate the volumes of a region on a Cartesian plane that's rotated around an axis. Okay, so I described what the disk method was and what the shell method was. Okay, so it is always wise for us to kind of visualize this I guess space, and we're going to visualize it by using a Cartesian plane. Okay, so let's minimize out first. Okay, so we have a Cartesian plane. Let's see here. We have our circle. Let's see here. Okay, I'm going to try to center this circle as best as I can. Alright, this looks pretty centered to me. Okay, so we can represent this region or this volume as this circle. Okay, so first of all, we know that this circle should have a radius of r. Okay, so we're just going to write out all our axis points first. So this is axis x, this is axis y. So we know that this circle has a radius of r, so I'm going to write that down here. 0 to r. Okay, we know that this function is defined as x squared plus y squared equals r. Okay, squared. So if we were to take a, I guess how we would call it, a sub length of this, or like go into this quadrant of this circle and draw a line. Here, let me draw a line here. So we're going to go to one of the quadrants of the circle, and we're going to try to bisect it or cut it in a way, and we're going to describe this length here as h. So this length, resultant length here, is oh sorry, this length should be h. Sorry. And this point here should be 0 and r minus h. Alright. Okay. So if we were to take this region, I'm going to color it in a bit. If we were to take this region of this circle in a 2D plane and rotate it around the y-axis, we would get the region that we so desire, and we can calculate the volume of that. Okay. So what we're going to do is, let me just rotate this first for you guys. Get a different color. So if we were to rotate this region around the y-axis like this, we would get our volume at the top, right? This illustration here. Okay. So like I described in the disk method and the shell method, we are now going to find a area. We're going to add the area of a cross section of this, I guess, this cap, and we're going to sum up all of these areas. Okay, so a rule of thumb when you're describing the disk method or the shell method and seeing which one you should use, you should always describe what you have as a differential strip. Okay, so the differential strip is just and what I guess way are you differentiating. Okay, in this case, our differential strip is perpendicular to our point of rotation. So we're going to use our disk method here. Okay, and what we're basically going to do is we're going to use the disk method, which I'm going to write out now, and it'll make more sense. Okay, so the disk method, so the area of our volume or described solid S is equivalent to the integral from I guess b to a of pi r squared, or the area of the cross-sectional circles of this cap. Okay, in terms of, I guess, dx. Okay, so if you think about it, if you rotate this around, we will have a radius of cross-sectional circles within this circle, right? If you rotate it around. So basically our strategy here is to add up all these circles within this region, and that will be equivalent to the volume of our described solid, okay? Okay. So first of all, we have to define what our radius is, okay? So our radius here is, so this is also r and 0. Our radius can be described of our differential strip of our circles as, okay, so I'm going to call our radius xr, not r, okay? So not to be confused. Our radius can be described as the difference between this y value here and the radius at the top, okay? So that can be defined as our radius, okay? So we can define it as the square root, which is the I guess the distance function of r squared minus y squared, okay? So if you think about it, this is our radius here, and this is the radius of our circle. We can say that the distance will be r minus y, okay? And by doing so, we can plug this into our equation here. I don't know why I wrote s here. This should be v. Okay. And now we can write our whole equation. So let's say here, so v equals, so we're calculating the integral from r to r minus h, okay? So r to r minus h. And we're going to be integrating in terms of y, all right? Because we're using the variable y here, okay? So it's going to be r squared minus y squared dy, okay? So this integral here, once we solve it, is going to be equivalent to the volume of our solid, right? So if we were to simplify this, we would get rh of r squared minus y squared dy, okay? And if we were to integrate this further, we get, we're going to use our power rule here, so we get r squared y minus 1/3 y cubed r to r minus h, okay? Also, don't forget our pi here. We're going to write our pi. I forgot that. All right, so now we're going to need to evaluate this definite integral. Okay. So our definite integral will be pi of r squared times r minus 1/3 r cubed. Okay. And that will be minus r squared r minus h plus 1/3 r minus h cubed. Okay. Let me just see that I calculated all this correctly here. R squared minus. Yep. Okay. All right, and that would equal to. So we'll take out the pi over 3 here. So we'll get 3r cubed minus r cubed minus r squared r cubed plus r squared h, and then the expansion of this, which is 3r cubed minus r cubed minus 3r cubed plus 3rh. And then this is just minus 3r squared h plus 3rh squared minus h cubed. Let me just see if this is correct here. 3r cubed minus r cubed minus 3r cubed plus 3r squared h minus 3r squared h plus 3rh squared minus h cubed. Okay, I think I got it all there. Okay, and simplifying all these terms together, we get pi over 3 of 3rh squared minus h cubed. And if we simplify this even further, we get pi h squared over 3 and 3r minus h. Okay, cool. So let me just run through the problem again because there's a lot to describe and maybe you guys are confused. Okay, so the original question was to ask us to find the volume of this solid, which is a cap of a sphere with radius r and height h. Okay, so we illustrated this this solid in a two-dimensional form, and we reasoned that this solid, the volume of this solid, is equivalent to this quadrant region that is revolved around the y-axis. Okay, and now because of that, we reasoned that if we were to add the cross-sectional circles, so if we were to do a cross-section of this, we would have a circle with radius r, right? Okay, and we reasoned that this radius r can give us the area of that cross-sectional circle. And if we were to add up all those cross-sectional circles at different cuts, we would find the volume, right? In the same way, we reasoned that if we were to calculate the cross-sectional space, then we would need to find this differential strip, right? Because now we're thinking about, okay, so the radius is changing constantly, so we need to find the radius of these cross-sectional circles, right? And the radius of those cross-sectional circles are found by the root of r squared minus y squared. Okay, so we just used the distance equation, and we were able to find our radius. Okay, so now using our disk method, because the rule of thumb is that if our differential strip is perpendicular to our axis of rotation, we can use the cross-sectional addition method. The shell method suggests that we use a cylinder method instead, and we add the surface area of all those cylinders. Okay, so we defined our volume of our solid as the definite integral of the cross-sectional circles, of the areas of the cross-sectional circles. Okay, and by doing that, and by defining our radius of a differential strip, we're able to come up with this integral here. And then we are just able to solve for it and calculate and simplify to find our equation to find the volume of the cap of a sphere, which is pi times h squared divided by 3 times 3r minus h. Okay? So yeah. And let me just add a bracket here. Okay? So that's how you solve the problem. So